He asked. Okay, so let's get started with a little review. What two things do you need to make a buffer? I'm kind of chilly. Weak acid and conjugate base, or weak base and conjugate acid. Not yet, but it's the same. What purpose do buffers serve? What do?
They minimize pH.
Okay, they resist pH change. Basically, when a system is buffered, it's going to be able to maintain its pH very close to where it started, which is a good thing. Okay, we've talked about that quite a bit. What are some examples of pairs that could make a buffer? Go ahead, write some random things down. I suppose you'd have to think of some random weak acids or weak bases, but try to give me three-ish, if you could. Write down some pairs. What two substances would be needed to make a buffer?
HC2H3. That's the acid.
Mhm.
Acid, and then without the H,
You can call people Graham's way. Nobody does. Everyone's way. I don't think I got called for that. What if you got? Okay, well then you're probably going to the hospital.
Give me some examples.
oh, I did ammonia and ammonia. Not the acid,
Ammonia and ammonium. Now, ammonia is a pure substance. I can add that directly. How would I introduce ammonium to my buffer? Is there a jar or a bottle of ammonium in my chemical storeroom? No, those ions don't exist independently.
Why not?
It's just not stable. They react with something. If they do exist for a split second, they instantly react with whatever's nearby.
So then how is it?
How is it a thing? That's kind of what I'm asking. It needs to be attached to something else. So if I want to introduce ammonium into my buffer, generally what I would do is I would add a salt compound that contains ammonium. For example, I could add ammonium chloride. That would work. Why is chloride a good choice for my anion? Because it's neutral. That's a great choice. I don't want my other ion to mess with pH at all, right? If my other ion is messing with the pH, well, then my buffer is going to be screwed up. I want the other ion to just be neutral and I mean, I need it, right? Because again, I need the ammonium. The only way I can get the ammonium is if I'm adding it in the form of a salt. Okay, what else? What's another pair? That's it? The only buffer that exists? All right, good job, guys. That is acetic acid.
And then is it acetate?
Acetate. Now, again, kind of like the ammonium, how can I introduce the acetate into my buffer? That's not a thing. That's two negative ions.
Oh, word.
Word.
Yeah.
Word.
Add sodium.
Yeah, okay, so I need salt, right? Again, I can't just go into the back chemical storeroom and find a jar or a bottle of acetate. It doesn't exist. The acetate needs to be with something else to be stable. So sodium acetate would be good. Potassium acetate would be good. Something along those lines. What's another pair? Can you name another weak acid?
No.
Sure, there's a whole bunch of weak acids. There's a ton of weak acids.
Is cyanide?
HCN, hydrocyanic acid, yeah. You want to make a cyanide buffer? Sure.
Yeah. Can you explain it in detail, please?
Nothing to explain, it's just that stuff. It's easy.
Well, that's
Again, as long as your acid is weak and you also have its conjugate, it's a buffer, right? So this is, I guess, a matter of can you name more weak acids, which evidently we're struggling with.
Wait, what's a weak?
oh my god.
Like the definition of a
No,
weak
like,
acid?
how do you know?
Is it one of the 6?
Yeah, but I don't know the 6. So
Well, then there's your problem.
Jack. Jack.
The 6 strong acids are HCl, HBr, HI, HNO3, HClO4, and H2SO4. It's not one of those 6, it's weak. HClO3, HClO2, HClO are all weak acids. Any of those can make buffers. Phosphoric acid, H3PO4, you can make a buffer from. Tons and tons and tons of weak acids exist. Okay? Tons of them. And it doesn't really matter. As long as it's weak, you can make a buffer. All right, we'll just leave it there for now. That's fine. If I have equal concentrations of a weak acid and its conjugate base, how are the pH and pKa related? If I have equal molarities or equal concentrations of weak acid and its conjugate base, how are the pH and pKa related? That's your weak acid, right? That's your conjugate base. Okay. Again, A is just a placeholder, right? If I go back to the previous slide, HA could be acetic acid, where this is your H, and this whole anion is like A, right? And then the conjugate, what's the conjugate? You just remove the H, and you have a 1- charge. So there's your A, 1-, HA, A, 1-, right? So A is a placeholder. A just can be substituted for any weak acid. What is the pH and pKa relationship here at this point in time? If acid and conjugate base are equivalent, these are the same. Okay? At the halfway point of a titration, which is what I gave you in the hint, pH and pKa are equivalent. What's also true at that spot? Weak acid and conjugate base are equivalent. Okay? These relationships are really important. They help a ton. They help us kind of problem solve through a bunch of different acid-base problems. Understanding how pH and pKa are related, understanding how the weak acid and its conjugate base concentration are related, help us a lot in terms of like our understanding of acid-base chemistry. So if these molarities are equal, I'm at the halfway point, which is the spot of a titration where pH and pKa are equivalent. Okay, let's introduce our equation. When we have a buffered solution, more often than not, there won't be equal concentrations of the 2 acid-base species. Okay, the one we did yesterday, the buffer we looked at yesterday was 0.5 molar acetic acid, 0.5 molar sodium acetate, and we had equal concentrations of acid and base. That's not always going to happen. Okay, if it does happen, what can we do? If I want to solve for the pH of a buffer where the acid and the conjugate base have the same molarity, I just solve for the pKa, and that's the pH. We're good, because that's the halfway point. So if you remember from yesterday, we solved for the pH of our buffer, and we did a whole bunch of work. We did a nice table, and we did all sorts of, we set up K, and we set K equal to the X values, and we solved for X, and it was a pain. And then by the time we were all done, we just got a pH equal to the pKa. All right. If you have equal molarities of acid and base in your buffer, pH equals pKa. But more often than not, they're probably not going to be the same. Okay, so let's look at this equation. This is called the Henderson-Hasselbalch equation. You can call it the HH equation if you'd like. I don't care. For whatever reason, it sometimes gets called the David Hasselbalch equation, which is very obviously not the person that should be credited for it, but
I like that.
you like that? Excellent. Henderson-Hasselbalch is the appropriate name of this equation. This is in your periodic table. Well, I guess it's your periodic table, your formula packet. Okay, it is in there. Where are we? There we are. First page of equations. Second one up from the bottom. pH equals pKa plus the log of A1 minus over HA. If you make a buffer with equal concentrations of weak acid and its conjugate base, what is the fraction of A1 minus over HA equal? If I have a buffer with equal concentrations of weak acid and its conjugate, weak acid, conjugate, it equals 1, right? Okay, if I have equal molarities, this is 1. So what's the log of 1 equal? If you take the log of 1, it equals nothing. So if I have a buffer with equal concentrations of A1 minus and HA,
It's just the pKa.
pH equals pKa.
Oh, because it's a.
Because this whole term just turns into 0, right? That makes sense. That's good. That's exactly what we've been up to anyway with everything else that I've been talking about. So this is the Henderson-Hasselbalch equation. We're going to use it a ton. pH equals pKa plus the log of A1 minus over HA. Now, to make your life a little easier, you might want to call this base. You might want to call this acid, because sometimes it gets confusing as to which one should be on the top and which one should be on the bottom of your fraction. It can get a little confusing. So sometimes I will verbally say this as pH equals pKa plus the log of base over acid, because sometimes identifying which is sneaky. Yeah.
You mean with the conjugate, right?
Sure. The term conjugate is just implying like a pair
Yeah.
between the two of them. So whether I call this base and conjugate acid or acid and conjugate base is kind of the same. Meaning, like, if I call one of them the conjugate, the other is a part of that pair. So yes, to make life easier, I'll just call it base and acid. Now, does it need to be a conjugate pair? Yes, it does. So one of them is the conjugate of the other. But which one I call the conjugate is irrelevant, if you're following my logic. Okay? So base over acid. Now, this equation can only be used for buffers. If I don't have a buffer, this equation serves no purpose, and it will not help us solve anything. The Henderson-Hasselbalch equation is only for buffers. If you don't have a buffer, this is not your choice. You can't use it. When do we have a buffer? Weak acid and conjugate base at the same time. So yesterday, I did like an ABC, the one problem where it's like, hey, does this create a buffer? And A was yes. And then it's like, hey, does that create a buffer? And B was no, and C was no. For part A of that problem from yesterday, to solve for pH, I could have totally used the Henderson-Hasselbalch equation because I had a buffer. But if I don't have both things, if I don't have both acid and conjugate base, I cannot use this equation. This equation is only for buffers. So please, I beg you, we're in buffer world right now. That's what we're kind of focusing on right now in this unit. But once we go back to some old stuff, this equation is kind of nice and it's friendly. So then a lot of you want to try to like use this for everything, but it doesn't work for everything. If you want to solve for the pH of a weak acid, you got to use an ice table. If you want to solve for the pH of a weak base, you got to use an ice table. If you want to solve for the pH of a strong acid or a strong base, you can just take the negative log of its molarity. The only time this works is with a buffer. Okay? Hopefully I got my point across. So if I create a buffer with 0.5 acetic acid and 0.5 sodium acetate, same one we did yesterday, let's use the Henderson-Hasselbalch equation to solve for pH. Yesterday, what we did was set up an ice table, set up K, used X in our ice table, solve for X to solve for pH of this thing. It was kind of a pain in the butt. Today, since we have a buffer, we're going to use this equation. Oops. Okay, they gave me Ka. How can I solve for pKa? Hold on, I'm going to calibrate this. I'm getting some weird. Not very difficult. Negative log of Ka. Take the negative log of 1.8 times 10 to the negative 5. What does the pKa equal? I think that's what we had yesterday, right? 745. Okay, so pH equals, sorry, 4.745. And then we have this other factor. We have the log of our base over acid. Our molarity of base is 0.5. How can I recognize that this is my base, right? That's maybe the hard part. That's salt. But remember, that salt contains the ion of our conjugate, right? Acetic acid is the acid, obviously. And the other portion of this is sodium acetate. Acetate's our conjugate base. So the molarity of that is 0.5. And the molarity of our acid is 0.5. And this is our setup for the Henderson-Hasselbalch equation. The log of 1, because 0.5 over 0.5 equals 1, log of that equals 0. So what does our pH equal? 4.745. Now, that's the exact same answer we got yesterday using an ice table, setting up K, doing that whole thing. But the Henderson-Hasselbalch equation just streamlines the process and gets us right to the pH without having to do an ice table. Because I wanted you to understand.
What is David? David Hasselbalch.
He's a German actor. He was on Baywatch. He was the main guy on Baywatch.
Look up a picture of him.
And he was also in the SpongeBob movie. And he was the one that SpongeBob and Patrick were on his back and he was swimming across the ocean.
That's like the best movie scene.
Cinematic.
Remember? Then I'm David Hasselbalch. Yeah. If you don't think I've seen that movie, I have a 7-year-old son. I've seen it. To create buffers with different pH values, you can use a different concentration of weak acid, but it's usually easier in a lab just to add more or less of the salt. So for example, right, let's say I have a jug of 0.5 molar acetic acid. Okay, random? We might have them back there. It's not that random. No. So if I have 0.5 molar acetic acid, if I want to change the molarity of my acid, it's kind of a pain, right? If I want to make it more concentrated, I would need to add more acetic acid in its pure form, which isn't very friendly stuff. So it's not going to be very viable. It's going to be a pain. If I want to make my acetic acid have a lower molarity, then I have to add water and do a dilution. Also a pain. I just gotta add, you gotta calculate it out, add water, mix it nicely. It's just kind of, eh. So when you make buffers, it's usually easier just to add more or less salt, right? My salt contains the conjugate base. If I want my buffer to be more basic, I just add more salt. If I want my buffer to be more acidic, I just add less salt. And that's usually in the lab with the easier of two paths when you make a buffer. It's easier to just add more or less of a solid substance to a buffer than it is to like dilute or make the solution more concentrated. That's kind of a pain. So to make 750 milliliters of a buffer with a pH of 5.14, you will need to add a certain mass of soluble sodium acetate. The acetate concentration would be the A1 minus in the formula. Solve for A1 minus using the stock solution of 0.5 molar acetic acid. what I'd like us to do is make a buffer with a pH of 5.14. Our materials available are 0.5 molar acetic acid and solid sodium acetate. Okay, so this is a buffer. We can use the Henderson-Hasselbalch equation. Wow. Okay, same stuff, right? We're just messing with our buffer a little bit. We're going to change the pH of our buffer. Now, if we had equal molarities, our buffer is going to have a pH of 4.74. But I don't want equal molarities anymore. I'm going to mess with it. What do I know? I know my pH is supposed to be 5.14. That's the end goal, right? What's my pKa? That was from the previous problem, right? That's the negative log of the Ka value, which was given to us previously. Now, plus my log of base over acid. I know my molarity of acid. I don't know my molarity of base. That's the end goal. So the idea here is, let's solve for the molarity of base necessary to make this buffer have a pH of 5.14. Okay, that's the end goal. Now, in order to do that, we're going to have to get rid of that log. Well, we've been doing that a whole bunch, haven't we? We've unlogged quite a few things in this class. So let's do that again. I'm going to subtract 4.745. So I have 0.395 equals the log of A1 minus over 0.5. Now let's get rid of that log. How do I get rid of that? Ten to the power of both sides. What that happens over here then is the 10 of the log just cancel out, and I'm left with just what's inside that parentheses. On the left-hand side, obviously, that's just a numerical process, so I'll just get a number. So 10 to the 0.395 gives me 2.483 blah, blah, blah. And this is going to equal A1 minus over 0.5. So then I multiply by 0.5. And I'm getting a molarity of A1 minus equal to 1.24. Yes?
Yeah, I agree.
Let's recap for just a second here, right? What did we just do? The goal was to create a new buffer. This buffer was supposed to have a pH of 5.14. The molarity of the acid was kept the same, but we needed to calculate a different molarity of base necessary to create this thing. Now, the original buffer was 4.745, and the goal is 5.14, meaning we want our buffer to be more basic than the previous example. So it totally makes sense that our molarity of base should be higher than it previously was, right? That's just logic.
Yeah.
Okay. Speaking of which, if our buffer with equal concentrations has a pH of 4.74 and we want a buffer at 5.14, which relationship below should be true for our new buffer? Right? That one. Because what's HA represent? Acid. What's A1 minus represent? Base. Correct. Let's finish this problem. Let's calculate the grams of sodium acetate necessary to make this. No, it's not gross. It's fun. I would imagine.
Do you do this at home?
Do I do this at home? No, not usually.
Just for fun.
Not usually.
Okay, besides Rocket League, what are your hobbies?
I watch a lot of sports
Okay, and board games.
and board games. I love board games.
Do you play by
I have a room in my basement right now that has a gigantic board game set up, and I haven't taken it down in like 2 months.
Wait, like what kind of board games?
Are you asking what the board game is?
Yeah.
It's called Gloomhaven.
Oh, it's a single.
No, it's not a solo campaign. It's with my brother and his buddy. But
Wait, they call
the
it
box is like
Wait, like the
it's over $100 board game,
Whoa.
and the box weighs like 20 pounds.
He's in the big leagues.
Oh yeah, I don't mess around.
Is this where all your investments go?
So it's quite. I mean, it is a dungeon crawling board game with
like Dungeons and Dragons?
no way better. So it's an RPG style game where you have your character, but like you know, it's kind of like an RPG video game where you upgrade your character, you get new items, you do all that stuff. But like the combat in the board game is like super strategic and really fun.
Oh, so how's it? Is that
Great.
what makes it better than D&D?
Yeah, D&D is too freeform. I don't like the freeformness
Like
of.
too much imagination.
Yeah, that's not my style.
Yeah, imagination sucks.
I,
It's like all imagination.
Gloomhaven it's the #1 ranked board game of all time on BoardGameGeek.com.
Oh, that is
And if you're unfamiliar with BoardGameGeek.com, great website, best online community of board gamers anywhere. And do I have an account? Of course I do. Okay, that stirred you guys up. All right. Now, the end goal here is to solve for our salt. We want to solve for the mass of sodium acetate. Well, what do we know? That's a good question. What do we know? We know the molarity of the base that we want eventually, right? We want a 1.24 molar base solution in our buffer. How much buffer are we creating? 750 milliliters. We're going to start there. I have 0.750 liters of buffer. And in that 0.75 liters of buffer, I eventually want my molarity of base to be 1.24. Factor label, by the way, if you haven't figured that part out yet, right? Liters to moles to grams. Now, grams of what? What the heck are we adding? Sodium acetate. What's the molar mass of sodium acetate? You're going to have to look that up. So I suppose I should write the whole thing out, right? Instead of A1 minus. NaC2H3O2, which of course spells nacho. What's that? 82.034? Is there a second on that? Everyone just trusts Cole? Yeah.
What did you say it was?
I do kind of trust Cole. He's usually on it, right? Everyone screws up. I screw up. It's all right. How many grams of sodium acetate do we need?
Wait, what is that?
That's sodium acetate.
Nacho.
How many total grams? 3 sick pigs.
Yeah, let's see your point. 76.3. 76.3.
So if I were to add 76.3 grams of sodium acetate to my 750 milliliters of 0.5 molar acetic acid, I would have created a buffer with a pH of 5.14. Right? That's kind of the recap of what we're up to here. If I have equal molarities of acid and base, my pH equals my pKa. But in this instance, our pH is different than our pKa. We didn't want a pH of 4.745 like this. We messed with it. We want a different pH, right? Because sometimes you don't want the pH equal to the pKa. Sometimes you want your pH very specifically somewhere else. And if you just mess with the ratios of acid to base in the buffer, you can achieve that within reason. Okay? If I were to mess with this ratio, let me see where I want to go. That's fine. This ratio, HA and A1 minus, if I mess with that ratio, okay, to make a good buffer, you probably want them to be close-ish together. The further you get away from a 1-to-1 ratio, the worse your buffer is going to be in terms of being able to like neutralize other stuff, right? Because even already, even though we've only moved the pH to 5.14, if you look at the molarities, right? The molarity of my acid is 0.5. The molarity of my base is over double my acid. This base in my buffer could neutralize way more acid than the acid in my buffer could neutralize base. Sorry for the cyclical nature of my sentence there. Okay. But the idea here is a good buffer can neutralize both things. And the further your ratio gets from a 1-to-1, you're going to be lacking in one side of the neutralization and stronger on the other side, right? So a good buffer has the capability of neutralizing both things. So in an ideal world, you're always creating buffers extremely close to the pKa. The closer a buffer pH is to the pKa, the better that buffer is going to be. The further that buffer pH deviates from the pKa, the worse that buffer is going to be. Generally speaking, buffers should be plus or minus 1 from the value of pKa. So for this acid and base choice, right, this is acetic acid with sodium acetate, anything from 3.7 up to 5.7 is kind of appropriate for a pH, for a buffer of using this substance. But a buffer beyond 3.7 or beyond 5.7 using these two substances is going to be kind of worthless. Just kind of some side note. We'll talk more about that tomorrow. That's kind of tomorrow's topic too. But anyway, all right, let's do a couple more problems, a couple more things to think about. Using 1 liter of a buffer made with HNO2, that's nitrous acid, it's weak. HNO3 is nitric acid, that's the strong one. So we got the weak one, that's good, otherwise it wouldn't be a buffer. 1 molar HNO2 and 1 molar NaNO2, sodium nitrate. Answer the following questions. What is the pH of this buffer? Well, it's a buffer. Let's use the Henderson-Hasselbalch equation. Right? I'm assuming I gave you a Ka. That's nice. That's good. We need that. Yep, good teacher. What's the negative log of 4 times 10 to the negative 4? And my molarities are the same, right? So even if I add this, I get 1 over 1. I kind of like those other boards better. I like being able to erase with my hand. I make too many mistakes in this board. So the log of 1 is 0. So in other words, pH just equals pKa. So the pH of this buffer is 3.398. Yeah, well, if I gave it to you yesterday, it would have been a giant pain, right? But life's easier with the Henderson-Hasselbalch equation. If I add HCl to this buffer, what's the reaction that would take place? If I add NaOH to this buffer, what's the reaction that would take place? Write those out. Give me net ionic reactions for each of those processes. Go for it. I'll give you a couple minutes. Add it to the buffer. The buffer contains both things.
Wait, what's the? We got it, right? Yeah. We got it. That contains food.
How do you represent strong acid?
So this is salt. Yeah, and all the water. What is salt? So is it NaNO or is it NA1 plus and NO2 minus? Yeah. Do you care about the NA1 plus? No.
Yeah, 2, HNO2.
Wait, but that's this.
Yeah. That's what they do. That's what buffers do. This, I've shown you this twice already before this.
Really?
Yes.
I don't believe it.
Good thing I'm doing it a third time.
I'm just gonna guess.
Don't do that.
It works well. Like
Guessing?
today, huh?
Guessing works well.
Yeah, like today when I said, oh, it's probably like whatever.
That was good, actually, yeah.
That was like spot on.
Now, net ionic is the way to go. All right? Net ionic equation is really how you want to represent this. If I, just for the sake of argument, because I want to make sure that this is still making sense, because we've done this a couple times, but this is something you have to be able to do. Okay? HCl, strong or weak? Strong, it's going to dissociate, right? So how should I represent that? And if I really want, I'm going to include this just for now, okay? Now, what's the other reactant? When the acid gets added to the buffer, what's going to react with it? The sodium nitrite, the NaNO2. Now, NaNO2 is what? It's a salt, right? What do salts do when they're in solution or when they're in water? Dissociate. So how should I write this? Okay. What happens when these things mix? The acid will donate to the base. And I get HNO2. And what's left over? Why don't these come together?
They could.
And it's gonna be a salt, right? What do salts do in water? They dissociate. So even in theory, if this came together to make salt, it would just break apart because it's in water. They're strong electrolytes. So long story short, what do we end up with? We end up with H1 plus NO2 1 yields HNO2. Because this is a strong acid, this is a salt, which is a strong electrolyte. Dissociate. The chloride and the sodium are both neutral. The sodium and the chloride are both spectators. For the other one, if I add sodium hydroxide to the buffer, sodium hydroxide, strong. What happens? Dissociates. It's a base. Do we care about the sodium? No, it's going to do the same thing that this sodium did. A whole lot of nothing. So how am I going to represent my base? I'm just going to represent my base as OH1 minus. What's going to react with my base when I add it to the buffer? What inside the buffer is going to react with that? HNO2. How come I don't break this one apart? It's a weak acid. Yeah. Weak substances stay together. Strong substances break apart. If it's a strong acid, strong base, or salt, I break it apart. If it's a weak acid or a weak base, I keep it together. This is a weak acid. It stays together. So now, this is the acid. This is the base. The acid will donate to the base. And what do I get? I get NO2 minus, and I get water. Like such. If I want to be more complete, I should probably put phase tags on everything. Aqueous, 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 liquid.
That's a really.
Questions? You've got to be able to do that. You really, really, really got to be able to do that. When I say, hey, here's a random acid, hey, here's a random base, can you give me a reaction? You've got to be able to do that. Yes, 100%. And it's definitely going to be on the AP test too.
I'm getting more and more serious.
Good.
Yeah, it's all good.
Maybe then you're motivated to study, right? That's the.
I studied for the first time last night. Yeah.
Yeah. Yeah.
That's the point. They want to scare us. It's all like Friday.
Sure. I was going to post it yesterday. I'll try to do it today.
Yeah, I was kind of disappointed.
I know. I'm sorry. Well, we were up in the library, and then I had to go to Rocket League practice. You know, it was a whole thing. Okay.
Is that final you give up?
Yeah, that's okay.
That one counts your grade, huh?
Yeah.
All right, I'll keep it.
Yeah.
Using the same 1 molar nitrous acid solution, how many moles of sodium hydroxide would I need to add in order to produce a 3.6 pH buffer? This is involved. Okay, this is an involved problem. There's things to think about. So there's some pretty, we got to really make sure we understand what we have, where we're going, and how we're going to accomplish this. So first things first, the end goal is to figure out the moles of hydroxide required to create our buffer at a pH of 3.6. Okay. We know how much weak acid we have in our buffer, right? How much weak base do we want in our buffer? Let's figure that out. Let's use the Henderson Hasselbalch equation. Let's start there.
Wait, you don't know are we still using it?
Okay, so our buffer is going to be a pH of 3.6, right? They gave us that. What's the pKa of this acid that we just solved for from the previous problem? Okay. Plus the log of base over acid. I don't know my base. I do know my acid. My acid's 1. Let's solve for A1 minus, just to start this thing out. Once we know the molarity of weak base that's required, then we can deal with the other part of this problem. So I'll subtract that from this side. Where's my calculator? And I get 0.202 equal to the log of A1 minus over 1. I'll take 10 to the power of both sides to get rid of that log. And I have 1.592 blah, blah, blah equal to A1 minus divided by 1. Of course, I multiply by 1. That does a whole lot of nothing. So my A1 minus is equal to 1.59. I guess we'll keep the 3/6 bits. Okay. That's not what I wanted, right, though? That's the molarity of conjugate base that I need in order for this to be good. This is kind of a mean problem.
Yeah, we'll keep it tomorrow.
No, let's keep going. It's just going to be a pain in the butt.
Why? Well, we have this.
In order to make this buffer, I'm adding sodium hydroxide to neutralize some of the acid, right? Kind of, but here's the other problem. The other problem is that this molarity is bigger than the entire molarity of my acid. So if I'm trying to achieve this buffer, I can't add 1.59 moles of hydroxide because then I'm just literally going to completely neutralize my acid and just have extra OH. That ain't going to work. I don't think I have to. I went a little overboard with this problem. I apologize. It's fun, but
Oh yeah, it's so much fun.
Okay.
this ratio, okay, this ratio right here is 1.59 to 1. As long as I have that ratio, meaning like some number up top, some number on bottom, and that ratio holds true, then my pH will be 3.6 like I want it to be. So the question is how much of the hydroxide do I need to add in order to hit that ratio? That's the question. Okay? I think we're going to leave this. We could solve it, but in all honesty, this is beyond what AP is going to do to you.
This is beyond.
Well, because when I write things, okay, so sorry, Maddox, you're right. In my head, when I write worksheets and I give problems, I'm like, oh, this is really good. And then it's like, wait a second. And then I'm teaching it, and I'm like, wait, why did I put that in there? That doesn't seem very nice of me. Sorry. So I would want to make sure that I hit that ratio, right? In other words, I want to neutralize enough of the acid and create enough of the conjugate so that my ratio is 1.59 to 1 when I'm all said and done. So if I set up a mine table, I would have HNO2 plus OH. Okay, and this creates NO2 minus plus water. And I would have a mine table, and I would have 1.00, and then I don't know this.
Oh, we're actually doing this?
Huh?
I thought we stopped.
This is for fun.
Yeah.
This is fun. That's why I love it.
Okay. And the end goal down here, right? This right here, I need this to be 1.59, so to speak, and this to be 1. Or, yeah. You see how it gets tricky, right?
Yeah.
Because I don't know how much of, yeah, how do we do that?
How do you know? You have to set up a ratio. It's not gonna be exactly like different numbers.
Well, this is the way my brain's thinking about doing it, right? The way I would do this is, if it's a 1.59 to 1 ratio, right? What percentage is each portion of that? I would use percentages. That's where I would go.
Yeah.
You don't have to, but that's where my brain went. So I would do like 1.59 divided by 2.59 because that's the total, right? Correct. I need to take away 61 point, 4%. So if I make this,
0.386.
I think if I do that, I think it's correct.
Yeah.
Maybe not though. Let me check.
No, that should be right. Then you get 0.3.
right?
Yeah.
That's fun.
Okay.
So that's how, that now, that's really annoying. Again, that's not, I don't know, I think that's enjoyable. Yeah, what? Oh, here, where you headed? Oh, no, not that stuff again.
It's not over now. It's not over now.